Today we have the last lecture, and the contents of this lecture will not be asked from you. So this is just for fun, this last lecture, and it will be devoted to a topic which is not so popular, like, for example, many-body system of Kalot-Moser type, but nevertheless very interesting, at least from my point of view, because it concerns field theoretical generalizations of Kalot-Moser type models, when coordinates xi of particles, which were functions of time in Kalot-Moser system or Rosenard-Schneider, now they become functions of two variables. Another variable which is called x, and this is space variable, and t is time variable. So these are, and instead of xi, for not to mix it with this x, let us call them ui. Now there are at least two interpretations. One of them is just many-body system, in which, however, coordinates of particles depend on two variables, not one, but two. They may be called space-time or just two times, two different flows, commuting flows, integrable. This is one interpretation. Another interpretation is in terms of field theory, classical field theory. However, the systems may be quantized, but this is a separate topic. We will discuss only classical case when these UIs are interpreted as fields in two-dimensional space-time, and there is an interaction of this nonlinear interaction of these fields, and remarkably, integrability is preserved as a result of this extension to another dimension. Integrability is preserved, and instead of Lux representation, which was LM Lux pair, it was of this form, that time evolution, time derivative of Lux matrix is commutator of the Lux matrix with some other matrix M, which implies that this flow is preserved spectrum of the Lux matrix. So evolution is similarity transformation for the Lux matrix. In these field theoretical extensions, instead of this equation, we have something like Zakharov-Shabat, excuse me, dxm. So commutational representation of Zakharov-Shabat type. Now the evolution of Lux matrix is not isospectral, but still this commutation relations allows us to find conserved quantities in the standard way, which is common for many integrable systems with this type of commutational representation. There are at least two ways to suggest such field theoretical extension. And one of them, which is probably most natural, is to consider elliptic solutions of the same integrable hierarchies like Kp, Toda, but to consider solutions that are functions, elliptic functions, not of the x variable, not of the first time variable. Now I'm speaking about Kp, where T1 is identified with x, and what we did a few last lectures, we considered tau function as function of x, and it was something like in elliptic solutions product of sigma functions. This extension, in this extension, we consider more general elliptic solutions, which are elliptic functions not of first time, but of some linear combination of times. Say sum over I with some coefficients, some finite linear combination of higher times with some fixed coefficients. In this case, the tau function can be represented in the following form. It is some function of all times multiplied by exponential function of a quadratic expression dependent on this u times product of sigma functions of u minus ui, which are functions of, in general, functions of all times. However, we will restrict ourselves to dependence on only first two times when x is t1 and t is t2. And the result of this consideration, which I will show a bit later, is that these ui's are just satisfy equations of motion for this field theoretical extension of Calogero-Moser model. Similar story can be repeated for Rusinard-Schneider case. In this case, we should consider solutions, elliptic solutions of Toda lattice, which are, before we considered elliptic solutions, which are elliptic functions of T naught, which we denoted by x. But now we should consider more general linear combinations, and the tau function for such solutions has similar form. And for these roots of it, it is possible to derive equations of motion which will generalize Rusinard-Schneider system to this field theoretical case. Now let me show you some details. I will begin with Calogero-Moser case from Kp and consider solutions of this form. For the function which was called u small when we considered Kp, but now u small is this variable, so I will denote this Kp potential by U capital. This is second logarithmic derivative of tau function. And if the tau function has this form, then this U is of the following form. We should just differentiate this expression with respect to x as a applying the rule of derivatives of composition of functions. And the result can be written in the following form. This is Weierstrass elliptic function. Plus some unknown at this moment function c of x t, which comes from derivative of this factor. It doesn't depend on u, only on x and t. A few words about meaning of these terms. In the case when u is identified with x, as was before in the previous lectures, then u is x, then ui is xi, and this derivative, partial derivative with respect to x, is just 1. So this coefficient is 1. And this vanishes because second derivative of linear function is 0. So this term is absent in our previous case, but for this more general case, it is here and should be taken into account. You can see that this expression is elliptic function of u, because this Weierstrass function is elliptic by itself, and this here we have a constraint that sum of second derivatives is 0, and in this case this term is an elliptic function too. What we should do next is more or less the same as what we did for previously. Just to substitute this form into a linear problem, first linear problem for Kp. For this, we need also some ansatz for psi function. It can be easily written as a double block function with poles at ui with some coefficients ci, and this is Lamé-Hermite function, which was already familiar for you. This is a general form of double block function because coefficients are elliptic functions. But this one is elliptic, so it's excuse me. Sorry. So it is natural to find solutions among double block functions. Substituting all this and this into this equation, we have a rather long expression with a number of possible poles in the left-hand side. I will not give you all details. You will be able to find them in the lecture notes. There are already almost all lectures in written form in English, except this one, and I will put it on the site soon. This last lecture is not yet written. And cancellation of all poles here, there are highest poles are third order poles. They cancel identically. But to cancel second order and first order poles, we should impose some conditions to this coefficients, which is natural to unify in an n-dimensional vector with these components, and cancellation of the poles lead to the following linear system. This is a vector. With some matrices L and M. Previously, this first condition was equation for eigenvector of this L matrix. Now it is looks like this, that evolution equation. This was evolution equation in T, and this is similar to the second equation, but it defines evolution in X. Instead of condition that L acting to C is some Z times C, now we have this more general equation. And the matrix M here is of the following form. It is L squared plus partial derivative of this matrix L plus some matrix A. Let me write them separately. L Aj is of the following form. It looks like the Lax matrix for usual Calogero-Moser system, but with some differences. Where before this diagonal part was momenta of velocities of the particles, and now this coefficient Xi is of the following form. You see that for the simplest case, this guy vanishes. This is 1, and this is velocity. So we reproduce the standard case. And the matrix A is of the following form. it's not the term, non-diagonal, off-diagonal. This is diagonal term, and the non-diagonal is as follows. Now, to achieve compatibility of this system, we should solve the Zakharov-Shabat equation, which is compatibility condition for this overdetermined system. So we should substitute all this matrix L in this form and matrix M in this form, where A is given by this not so simple expression. Of course, the calculations, when you substitute all that in here, you get something very long and cumbersome. And it is not easy to deal with this. So it requires hard calculations, which I omit and give the result. By the way, to perform these calculations, some non-trivial identities for elliptic functions are required. You can find them in the lecture notes. And now I will show you the result. The equations of motion has the following form. Second time derivative is equal to, there are many terms. By the way, this function C is not yet known. It should be determined from some conditions which I will explain below. For now, it is just unknown function. So this is third derivative, and another x derivative is taken of all these terms. So the highest derivative is fourth derivative, x. It is not all. There are other terms. So you see these equations as they appear after solving this Zakharov-Shabat condition. You see that they are not so beautiful, like, for example, original Kalodzer-Moser equations of motion. Not attractive, by the way. You see that it is hard to make some order out of this. However, when we consider Rusinard-Schneider, the similar procedure for Rusinard-Schneider model, which I will show you a bit later, then in the case of Rusinard-Schneider, the equations of motion, which arise in a similar way there, are much more, have a very nice form. And this not so pleasant form comes from a sophisticated continuum limit from the Rusinard-Schneider nice expressions. To take continuum limit, not continuum limit, but the limit eta to 0, where eta, you remember this parameter, which can be interpreted as inverse velocity of light. When it goes to 0, we reproduce Kalodzer-Moser case. And if you tend eta to 0 in the Rusinard-Schneider equations of motion, which have a much nicer form than this, you get this as a result of complicated limit. In fact, to find this function, you should take into account that the sum of second derivatives over all particles is actually 0. This follows from the fact that that we started from elliptic function. This is one condition, and another condition is that which follows from this. The sum of first derivatives is some h which is constant. It doesn't depend on time. The value of this constant depends on particular solution that we consider. So then we can sum both sides of this equation, because there are n of them. I takes values from 1 to n. So we take sum over all values of I, left-hand side, right-hand side, and in the left-hand side we get 0 because of this condition. And this allows us to find this function c, which has the following form. H is that constant. What is V? I will write a bit later. And V is the following combination. It is a double sum over I and K that are not equal to each other. In fact, this function C is defined up to adding of arbitrary function of t, because this additional term is not determined from our conditions. However, this term, some function phi of t, does not change equations of motion. So without any loss of generality, we can put it equal to 0. Now you can see all of this in closed form. And these are equations of motion of the field theoretical version of Calogero-Moser model. First, it was obtained by this method from dynamics of poles of most general elliptic solutions. This was done in the work by Krichever and to his students, Akhmetshin and Lvovsky, in the beginning of almost 20 years ago. And they called this in their paper, which you can find in the archive, e-print archive. They called these more general elliptic solutions elliptic families. Now, let me pass to Hamiltonian formulation of this system. In fact, it is Hamiltonian, like the original Calogero-Moser system. However, now it is infinite dimensional Hamiltonian system. First of all, we need canonical variables. They are momenta, pi, which depend on x. X here should be regarded as an additional index like I, but it is a continuous index. So the Poisson bracket of momenta and coordinates, which also have two indices, discrete index I, which takes a finite number of values, and continuous index x. These brackets are 0, and brackets between them are as follows. And this is delta symbol with respect to discrete indices, and for continuous indices we should write here delta function. So they are canonical, continuous canonical variables. The Hamiltonian, which I denote by this calligraphical letter H, is an integral of the Hamiltonian density. This H is Hamiltonian density. The limits of the integral depend on boundary conditions, which we consider. They may be conditions on infinite line with zeros at both infinities, or periodic system, then the integral is taken over period. And the Hamiltonian density has the following explicit form. Here, this V is the same as this one. This term, the last term, comes from this function C, which we, where it is, there. So from now we should write the Hamiltonian equations. They have standard form. However, instead of usual derivatives, we should take variational derivatives. So time derivatives of canonical coordinates is a variational derivative of the Hamiltonian over momenta, and time derivatives of momenta is minus variational derivative of the Hamiltonian over coordinates. A few words about these variational derivatives, how we should understand them. The derivative with respect to pi is simple, because you can easily find that this variational derivative is nothing else than usual partial derivative of the Hamiltonian density. However, the variational derivative with respect to coordinate can be taken with care, because the Hamiltonian contains not only coordinates, but also their derivatives, first and second, in x. Therefore, using the rules of variational calculus, we can conclude that this variational derivative is expressed through the Hamiltonian density in the following way. This term is due to presence of first derivatives in the Hamiltonian, and there are also second derivatives which give another term. So using these rules, it is possible, after a rather long calculation, to find the Hamiltonian equations, which I will not write explicitly. They are long and not very instructive. And a good exercise, which, however, requires hard work, is to show that these Hamiltonian equations are equivalent to the equations of motion which I wrote before, which were written in terms of coordinates and velocities rather than coordinates and momentum. So now the story about Calogero-Moser here is almost all, and now I would like to show you some details about Rosenard-Schneider case. In this case, the tau function has the same form as a function. U again is some linear combination of higher times, but for simplicity we consider here only positive times, and all negative times are put equal to 0 for simplicity. And the tau function is some function of x and t, where x now is t naught. Again, exponential function of some quadratic form. And the main part is the product of sigma functions. The linear problem, the first linear problem for the Toda lattice is of the familiar form, where b, this function b of x, is expressed through the tau function in the familiar way. With this tau function, it can be written more explicitly as a sum of pole terms. U dot is time derivative of these roots, and they depend on x. and again plus some not yet known function c of x and t, but not of u. U enters only here in the first term. Again, the ansatz for the psi function is actually the same. These coefficients depend on x, and here we have Lamé Hermite function. You should substitute this and this into here, and this into here, and again try to cancel all poles to achieve the equality. This leads to a system, as usual, as we already saw many times. This leads to a linear system for these coefficients. And this linear system can be written in the matrix form. Again, we have unify components of C to a vector, and the system here we have matrix M. This system is overdetermined, and the compatibility condition for this system can be written in the following way. This is discrete, in fact, semi-discrete version of Zakharov-Shabat condition. So in X, it is a difference or discrete equation, and in time t, it is a differential equation. So it is semi-discrete. And the matrices L and M are of the following form. This is off-diagonal part, and the diagonal part is like this. Now you should substitute the matrix L and M in this form into this condition and try to solve it. Again, it is not so easy calculation. Nevertheless, it can be done. I will not give you any details of this calculation, just show the result, which has a much more instructive form than that for Kalot-Moser case. So the equations of motion are of the following form. And there is also an extra term which depends on this unknown function c. Now you can see, I hope you agree that this form is much better than what we had in Kalot-Moser case as a e to zero limit of this. How to reproduce original equations of motion of Rusinard-Schneider is just to put these derivatives equal to constants. Then you see that all this gives you except this term, but in that case it also should be put equal to zero. You can see here the similarity with original Rusinard-Schneider equations of motion. How to find the function c? Again, we should sum over I all these equations, and this gives the following result for the function c. Beta is some constant which is similar to the constant h. Remember, in the case of Kalot-Moser. It is a double sum over I and k. So here it is. This system is also Hamiltonian, but to write the Hamiltonian in explicit form, it is convenient to pass two lattice variables in the X space. So to introduce some lattice with the step eta and denote lattice variables. There are two indices, I numbers of particle, ith particle, and k numbers the coordinate on the lattice. So we identify it with ui of k eta plus some constant. So in this way we introduce lattice. So originally it was x, this distance is eta, and we number it k takes integer values. These equations can be easily rewritten in terms of the lattice variables. I will not do this and just show you the Hamiltonian. Again, the canonical variables are lattice momenta, lattice coordinates, and between them we have the canonical Poisson bracket. The Hamiltonian, again H calligraphical, can be written in the following way. Sum over all lattice. Suppose we have periodic boundary conditions with period n, and we should sum logarithms of Hamiltonian densities hk. Then this hk has a very similar expression to the Hamiltonian for the original Rosenau-Schneider model. It has the following form. So using this, you can substituting this into the Hamiltonian equations of motion, you can make the calculations and obtain Hamiltonian equations. And it is again a separate task to show that they are equivalent to these equations of motion in the Newtonian form. And the problem is to show that time derivative of this Hamiltonian density, hk, is can be expressed through this function c, which is now a function of the lattice. T is continuous, but k is a lattice variable introduced in this way. Okay, the limit eta to 0, in which, in principle, we should reproduce Calogero-Moser case, is not easy. It is rather sophisticated limit, which requires some care. Perhaps I will not explain it because it's better to follow the details in written form. And using Blackboard, it is maybe not useful. So in a few days, I will put the lecture the notes of this lecture to the site, and you will be able to follow the details. And now, this is probably all. Another interesting and separate theme is quantization of all these models. Because almost all models which we considered, Calogero-Moser, Rusinard-Schneider, their spin generalization admit canonical quantization, and then the dynamical variables are operators, and you have Hamiltonian, and the spectral problem is to find the eigenfunctions and eigenvalues of the Hamiltonian. It is a separate story. Perhaps this is a subject for a separate lecture course, and I hope that in some future I will be able to deliver such a course. And for this course, this is all. Thank you for your attention.